So John, we think, will be another great speaker in this line. And he's going to be speaking today on the mathematics of music and language.
Thank you. A little bit about the inspiration for this talk. This talk evolved out of teaching TAMS classes for 12 years, especially teaching pre-calculus to those students. And the thought that I had when teaching was, when we teach pre-calculus, when we teach trigonometry, it's almost always in the context of solving a triangle, boring stuff. Trig functions are used all over the place in mathematics and science, and I wanted to try to communicate that to my students that what they're learning in pre-cal is actually going to be good for something later on in the future, even if they can't appreciate all the details that instant to see that pre-cal is going to be top of pre-cal are going to be definitely useful. So this lecture is on the mathematics of music and language. Little intro here. So little class to start the program. And the idea was to try to inspire folks to see that topics of trigonometry have applications to sound, particularly music, and also to applications in phonetics and how voice recognition software works, eventually leading to the Fourier transforms. So I know everybody in here, most everybody here knows a lot more than pre-cal. However, I'm going to... Never mind. I'm going to pretend that you guys pretty much know only pre-calculus and maybe a smidgen of calculus. And we're going to build up on some ideas from just that basis to talk about topics in music and language. A few caveats. Some folks in here are going to be much better musicians than me, so don't throw rocks at me if you know more than music than me, because I assure you some people here don't. And also, some people might know more about linguistics than I do. If you do, don't throw rocks at me. I hope to get across the bare essentials of these topics without talking about any one topic into extraordinary detail that I personally could not talk about. So let's talk about some of the basic problems that you see in a pre-cal book. So this is a typical problem that comes in pre-cal. A temperature at a certain location follows a sinusoidal pattern. The high temperature of 60 degrees occurs at 4 p.m. and the low temperature is 32 degrees. Given that, predict the temperature at noon. Kind of your typical pre-cal question involving trigonometry. How do we go about solving something like this? And some people have been practicing their certification exams in pre-calculus, so they better know this. How do we go about this? Well, let's see. The high is going to be 30. The high is 60, so we'll mark that. And the low is 32. Let's mark that. And the high temperature is occurring at 4 p.m. So that point's on the graph. What else can I do? Oh, they're either very shy or they forgot their pre-cal. Okay, draw a sinusoid. How do I draw? How big should I make it?
I want to say 6.
6 o'clock? Okay, why?
It's supposed sinusoidal over 24 hours. The difference between 60 and 32 is 28 degrees divided by 24 hours. 76 a degree per hour. So after 12 hours, will be 4 a.m.
Yeah, that'd be more of a linear pattern as opposed to sinusoidal, calculating the number of degrees per hour. Okay, have thoughts?
Well, do we know that the pattern is supposed to repeat every 24 hours?
It's supposed to repeat every day.
Okay. So yeah. So then it'll be then the low has to be at 4 a.m. So
The low is going to be at 4 a.m. Okay, so for this to work, the period of the thing has got to be 24 hours.
Yeah.
Okay, so that's not stated in the problem, but for this pattern to occur every single day, the period is 24 hours. How do I get something special about the trig function if I know the period is 24 hours? Remember that? 2 pi over b. Remember that? 2 pi over b is 24 hours. So that means that b would be equal to 2 pi over 24, or pi over 12. So the pattern's going to go something like this. The temperature is going to have, let's put a cosine of pi t over 12. There's going to be something involving pi t over 12 in the answer. Now I chose cosine because I know the maximum value occurs at 60, and so a cosine graph starts at the peak, and so I'll choose cosine as opposed to sine. Could do sine if I wished. Okay, amplitude. What's the amplitude of the trig function? Not 28. 14. Okay, so the midline is going to be right here. And so it's going to be 14 this way, 14 that way. Okay, and one other thing I need to know is the vertical shift. Vertical shift is going to be 32. 46, the midpoint. So I'm going to add 46 degrees. That's the midpoint between the low and the high. Okay. So rather than having the x-axis being the midline is going to be 46 up. Okay. One last thing to worry about is the horizontal shift. The peak is starting not at 0, but it's starting at 4 p.m. So I need to write t minus 16 here to account for the fact that I'm starting, the wave starts at 16 as opposed to starting at 0. So with that information in hand, then I can start drawing the picture. It's going to go something like this. The low is going to be at 4 a.m. The next peak over here is going to be 4 p.m. the previous day. And to get the temperature at noon, now that the hard work is over, plug in 12. So the temperature at noon is going to be T of 12. It's going to be 46 plus 14 times the cosine of, plugging in 12, we get minus 4 pi over 12. So cosine of minus pi over 3 is a negative, is half, so it's going to be 53 degrees. And that's the temperature at 12 noon, assuming the pattern works. Okay, that's the kind of the typical pattern that our students see in pre-cal, and it is completely physically unrealistic to have the temperature oscillating every day, but that's the kind of pattern that we give our pre-cal students to kind of sharpen their skills. Something like this is much more realistic. Is there a way to knock the light out in front? You guys see the line up there? Barely? Barely? I'm a little leery about starting to play with lights. So let's not play with it just because I don't want to knock the lights up for everybody. What you see here is the carbon monoxide levels at the top of the Mauna Loa volcano in Hawaii. That is the longest continuously running observation site for monitoring carbon monoxide levels in the world. So 14,000 feet up, they've got an observation thing, and they measure the carbon monoxide levels every month. And in the 1957 is time 0 here. And so at the very end there is about 2003 or so when the last data point for this particular data set. There's more data collected ever since then. Notice the trend going upward. Okay? So it's not like I've got a perfect sinusoid. Also notice that there's a pattern like this. It's going upward, but it's cycling upward like this. That's the seasonal trend. So it's a little bit lower in the winter and it's a little bit higher in the summer. So there's a seasonal trend for carbon monoxide levels. But over the last 40 years, the trend has certainly been going up like this. So how do you try to fit something like this? Well, you could try to do just a straight up regression fit. Just fit the data to something. Here's a quadratic fit to the data, just simply using Excel to try to get a quadratic fit to the data. But that certainly captures the fact that it's going up like this, but it's not capturing the sinusoid. So to capture the sinusoid, one way to do that would be to just throw on a sine function at the end of it. Okay. Now notice what the role here is. For this problem that I did, the 46, well, let me go over here. The 46 served as the midline, and there is oscillation around the midline. For this function, that quadratic serves as the quote-unquote midline. That's your base pattern. And then around that quadratic, that's where the oscillations occur. So rather than having a constant 46 being the midline, we now have a quadratic growth being the quote-unquote midline, with the oscillation occurring around that. And that does a halfway decent job of capturing the oscillations. Not perfect, but halfway decent. Yep.
Wait, so the fact that you have a sine of 2 pi t instead of 2 pi t plus some number, that means that you're assuming that the minimum occurs at 0?
January 1st. Yeah.
Okay, the minimum, okay,
Yeah, the minimum occurs in January 1st.
okay.
Yeah, so 2 pi t, so my b would be 2 pi over 2 pi for 1. So the cycle there is 1 year long, as opposed to the problem we had here, which is 1 day long.